Thank you. Good morning. Today is August 23rd. This is the last week of classes. Okay, today we are going to complete the details of the calculation of the tertiary stresses. It's just a quick review because we chapter 4 solving plate bending problems. And then we have to go into combining stresses, okay? So we have gone primary, secondary, tertiary, but some of these in certain situations, they are combined. So we have to consider that. And the thing is that, okay, you combine it, how? We're going to explain how we do that. And finally, okay, let's suppose that you combine it. And how do you know if this stress, which is the result of this combination, it's low enough or it's very close to taking the material to failure? So we're going to say a little bit about that, okay? Then we have a very short topic, which is about transverse strength of the structure. It's mainly a description. And then we have to go into, for me, it's a good idea that since in the last part of your professional training here at the university, you have to deal with design, okay? In this course, we have mainly developed, so it's a good idea if we make a quick review in about 2 hours of some of the design principles that one of the classification society employs, okay? That's an extra topic, really. I think it's quite interesting that after we have reviewed all of these engineering tools to analyze structures, we would like to see how these tools are implicit in the application of the ship classification rules, okay? So we start, the idea behind that is that we start applying these formulations, not just as a black box, right? But you see the formulation and comes to your mind, okay, this guy is just talking about beam bending or something. Okay, you see the formulation and say, okay, he's worried about shear stress. In the web, he's basically considering a mean shear stress. Something like that. Okay, that's the message behind this part of this last part of the material. Okay, so let's complete chapter 5 here. I think it's this one here. Okay, and then full screen. Isaac, can you see my full screen? Isaac, can you see my full screen?
Yes, doctor.
Okay. Okay, so we are here. How many students do we have right now? Isaac, how many students do we have right now?
15.
How many?
15. 15.
15, yeah. Okay, so it's total of, yeah, here it is. A total of 17, including you and me, so it's 15. Okay, so let's go on. In here, this is a summary of what we have done in the last 2 chapters, right? This is a secondary, it's a plate, reinforced plate panel, right? All of these. And here, I have one of these longitudinals. This is the simplest way what we can do. We can assume that one of these stiffeners, since they are smaller, much smaller than the girders, we can assume that they are clamped on both ends. Okay, we know that it's not complete, but as a primary quick analysis, we can apply that. But then the material between stiffeners, that's a plate. So that's the tertiary behavior of the structure, okay? So that's the equation that we solved in chapter 4. And in the end, we could consider that it is clamped on all ends. So that means that deflection and rotations of the edges are 0. This rotation, especially this rotation, null rotation, we can defend it because we have the plate, we have the stiffener, and when you apply the load, this will deform like that. So you see that it's here, it's like this, and now it's like that. So this rotation, okay, prevents the plate from being completely clamped. Okay, so that's that. Okay, and this is the Timoshenko material. This is the expression that we can apply if we want to analyze. So from this expression, okay, according to the aspect ratio of the plate, we get this constant. So we could estimate the moment, and with the moment and the thickness, we can calculate the stress. Of course, this is a maximum stress. That's analysis, right? If we want to go to design, we need to choose or select an allowable value for the stress. I mean, that's the limit of the stress. According to the loading and according to the aspect ratio of the plate, we could estimate the moment. And from there, we can estimate or calculate the thickness, the required thickness, okay? We can rewrite in this way. This is very useful because when we see the expression that we have in the classification rules for the thickness, there's a lot of similarity with this. So A, okay, according to the symbology employed in Timoshenko book, A is the lower dimension of the plate. Usually in our chapter 4, we said that A over B is larger than 1. So B for us in chapter 4 was the largest, the smallest dimension of the plate. So we have to be careful. P is the pressure and sigma is the allowable stress. You see that if you increase the sigma, for example, in a military vessel, in a naval vessel, right? What you can do is you can try to reduce the thickness. If you reduce the thickness, the weight of the structure is reduced. How can you do that? Employing a steel that has higher tensile properties. Okay, that's what we call higher tensile steel, HS, higher steel. And that means that the sigma allowable is not 235. Okay, you can reach, for example, 270 or even above 300, right? So if you increase this, that means that you could use lower thickness for the plating. If you use lower thickness, that means that the structure weighs less and you can carry other things on board, okay? But for us, this is common value of 235. That's what we saw there. Here, this is the expression that we see in the classification rules. We are going to review this maybe today or on Thursday, okay? And you see that this expression here, it's a constant A square root of P square root of sigma. And that's what we have here. It's a constant S, that is spacing, square root of P square root of sigma. So basically, this is an application of the previous relation that we deduced in chapter 4. Basically, that's what it is. Now here, they included a corrosion allowance. We explained why it's needed. And also, they say that the thickness has to be also higher than this value. So you calculate both, okay? And the thickness has to be higher than any one of them. So you take the larger value, okay? So this expression for me, we'll explain that in a minute. I think it's basically like considering that the plating has to support pressure, but also there are some situations in which there is more or a different loading applied on the plating. And the plate has to support both situations. So you have to calculate both. Okay? Since you have to support both, what you have to do is take the higher value for the thickness. That basically that's the idea. Okay. Now here about the allowable value of sigma, this is very interesting, right? Because if you increase the z is the sectional modulus of the whole, okay? So if you increase z, this z here, that means that the primary stress, for example, on the deck or on the bottom, reduces, okay? So if you reduce the primary stress, that means that you could increase the secondary or tertiary, in this case, tertiary stress. That's what we're saying here, right? So if you have Z over B, ZB over ZR, okay, higher, that means that you could increase this value, and that's the allowable value for sigma. If you increase sigma, that means that you could reduce the thickness T. Okay, so that's a very interesting thing. Okay, and this is also very interesting to see that there is a difference between transverse stiffening and longitudinal stiffening. And the thing is that in this case, for example, okay, this would be a transfer stiffening system, right? And in this case, this is a larger bending moment. So in this case, the tertiary stress will be pointing in the X direction. So that's going to be combined with the primary stress, okay? And you see that's here. In the longitudinal stiffening, you see that this value, the maximum value is 120. And that corresponds to the maximum, to the common value for the longitudinal stiffening. Why? Because in the longitudinal stiffening, the tertiary stress is pointed in the Y direction. That's the most important. Okay, there is also some stresses in the X direction, but we know from chapter 4 that those values are much smaller than in the Y direction. So that's start make some sense. Okay, here I try to show you that this is the normal stress distribution in the X direction. Let me write this here. This is X, maybe you see here. Okay, this is X, and this is Y. Okay, here it says that this is on the top of the plating. Okay, and you see that there is a, here, this is a blue, so this is negative, and this is positive. This is negative, and this is positive, and so on. On the bottom, this is the, here says the bottom. You see that in here, okay, in here, it's positive. Okay, so in the top, it's negative, and in the bottom is positive. Then you go to blue, which is negative. Okay, originally positive, in the top was positive, in the lower side was negative. So you see that that's a typical plate bending response. Okay, that's a result, remember, of the kinematic hypothesis. On the thickness, you have a linear distribution of stress. On the top and in the bottom, you have most probably about the same value, but the sign is the opposite. That's what we're seeing. Okay, and the other thing that we're seeing is that here and actually here, about this value and about that value. And they are about the same, okay? If you had completely clamped plate, you would have that on the edge, the stress would be twice the value that and the center of the plate. Not in this case. Why not? Because there is a redistribution, because the stiffeners, which are on the edge of the plate, they also rotate. If they rotate, that means that the edge is not clamped. Okay, so that's causes this redistribution, and basically, eventually, on the edge and in the center of the plate, basically the stresses are the same, basically. Okay, hopefully we will do an example about this in the next semester on the elements. Okay, so that's something that we have to have in our mind, and that comes this thing here. Okay, here, because I'm trying to relate the knowledge from chapter 4 and see how the classification societies are applying this. Okay, so here, what I did was I took this spacing. This is what we call S. This is S. And we took it equal to 0.6 meters. So this is a typical value, right, about this. Okay. And then what I did was I just changed the value of the spacing in the other direction. Okay. So this is L. So it's like S is the spacing between stiffeners and L is the spacing between girders. Okay. So I go up until 3 times that. Then I apply this formulation from DNV. Okay, so I calculated. Let me go back. This is what I'm applying. Okay, this is KA, which depends on SL. And once I have KA, okay, S is fixed, pressure is fixed, I could calculate the thickness. Okay, so that's what we're doing here. Okay, so this is the required thickness for the plating according to the aspect ratio of the plate. Okay, of course, if we have both, in both directions, we have a smaller spacing, we could reduce the thickness. So, yeah, you could say I could employ very close stiffness, but the problem is that you require more welding. So that would imply more money for the welders. And also, remember that every time you weld, they get distorted. So you have to get an equilibrium between these two ends. But in general, okay, this is what we're saying here, is that as you reduce the spacing between stiffeners or girders, you will see that as a result, you will see a reduction in required thickness and less weight. But you have to be, you have to find a compromise. Now, then we apply Timoshenko's results, okay? That's in this direction, in the Y direction, okay? So evaluated on the side here and also at the center here. And these are the results. So we applied the estimation of the thickness using Timoshenko results, employing the same pressure, the same sigma, and the same S value. These are the results. Here, we have the solution in a graphical way. Okay, up here, okay, this is the required, assuming that the plate is clamped, and this is the thickness that we will require if we will assume that it is clamped, and we take the largest value, which occurs in this point here. So we require more thickness than in these two cases. In this case, these two cases, green and blue, we apply the formulation from DNV. That's the blue. And in the green, we apply this formulation at the center. And we see that they are very, very close. So my conclusion is that when we have plate with stiffeners, right? The plate is in some way, okay, they are kind of clamped, because we see this behavior that on the stiffener we have positive, and on the center we have negative. Then we go back to positive. So that's in certain sense give you the idea that we are analyzing a clamped plate, but it's not completely clamped, because the stiffeners, when they deform, they also rotate a little bit. And that produces a redistribution in the bending moment on the plate. And as a result, more or less, the stress in the y direction on the edge and at the center of the plate basically are the same. That's the idea. So if we take the stress at the center of the plate and we select the thickness with that level of stress, we obtain very close result with that recommends the classification society. That was the message that we discussed last class. Any questions so far, people? Any questions so far? Questions? Okay. So now let's move to what we need. And what we need is, okay, we have shown ways, or well reviewed, ways to calculate primary stresses, secondary stresses, and tertiary stresses, right? But the problem is that we see that, for example, in some cases, we see that in the x direction, we have primary stresses and also secondary stresses. So we cannot allow the stress level to reach 235, because in general, that would produce a failure. So we have to start thinking about those trends, okay? That's the idea behind this part of the material. So this is the general situation. Okay, have a ship, and we see here, I have waves. That means that we have dynamic pressure, hydrostatic pressure, and we have the weight, and because it's dynamic pressure, there is an acceleration. So all of that produces a general loading on the hull. Okay, what we have done is we have split it in three. So we said, okay, let's consider the primary response. And basically, we're considering the hull very long as a hull, as a beam. So we can consider still water. We could approximate somehow the response on waves, and we have come out with a value for the bending moment. If you have a value of the bending moment, okay, you could calculate the stresses on the deck. And that's why we use super 1. That's primary. Okay, this x is this x. Okay, x means aft forward direction. Okay, I put it in the vertical direction, I put z, and I is in the direction of the beam. Okay, so in this case, this sigma x1 points in the x direction. Now, what about the secondary? Okay, now the secondary, for example, is a combination. It's a combination of plating plus stiffeners and girders. Okay, so in this case, okay, we have this, whatever, it looks like it's a stiffener, it's a longitudinal. So because of the bending of the reinforced plate, okay, this bending moment is also generated. So on the plate, this plate is the same as this plate. We're going to sigma x secondary. So this is primary, this is secondary. And we see that this and that are pointed in the x direction. Okay, now we have to be careful because this primary stress could be positive or negative. Okay, and the secondary, again, because the loading is pointing downward, okay, we're going to have a moment in this direction, and this is going to be compressive. Okay? But especially this one here, we have to be careful because that could be positive or negative. Okay, in what case, hogging or sagging, we have these stresses positive, people. Do you remember? Miss Avilés, are you there, Miss Avilés? In what case these stresses will be positive, hogging or sagging? It's a classical question for the evaluation. Miss Avilés, you're not here? Please. Are you there? No? Miss Dominguez, in what case, please, Isaac, please take her, Miss Aviles, outside of from the classroom because she's still here. Thank you. Miss Dominguez, in what case, we would have positive primary stress on deck, hugging or sagging? Miss Dominguez, hugging or sagging? Miss Dominguez, please wake up. Positive or negative? Do we have any message from Miss Dominguez, Isaac? Because I see that she's turning on and off. Okay. We'll let him suffer. Mr. Paredes, Daniel Paredes, tell me, in what case can you expect positive primary stresses on deck, hugging or sagging?
On the deck.
Yeah, on the deck.
In sagging.
In sagging. No, I think it's in hugging.
Oh, sorry.
No, no problem. Don't say sorry. Don't say sorry. So it's having like that, right? So we're going to have a crest here. So we have extra buoyancy in this area. And this, in this case, on the deck, we're going to have tension. Okay, so what I'm saying is that primary stress could be positive or negative. Okay, now let me erase this because I don't want to get any more. Okay, now, finally, what about the tertiary? We have to be careful because in general, in the tertiary stresses, plate bending, we have stresses in X or in Y, right? But what we have insisted is that in one of the two directions, in the direction of the shortest side of the plate, the stresses are much higher. Okay, so in this case, for example, that you're seeing here, okay, okay, since this dimension is much smaller than this dimension, that means in this direction, we could expect the tertiary stresses to be higher. So this moment will generate stresses in the Y direction larger than in the X direction. Okay? So that means that in this case, which is a longitudinal framing system, sigma Y will be more important than sigma X for the tertiary case. So, but that's in the Y direction. So we could calculate this sigma Y tertiary. So we have 1 and 2 in the X direction and 1 in the Y direction. How do you evaluate the primary stress, Mr. Gomez? How do you evaluate the primary stress? This thing here. How do you evaluate this, sigma x1? What information do you need in order to evaluate this?
Good morning, doctor. I don't remember.
Don't remember? Anybody? Mr. Chin Chin, how do you calculate sigma x1 in general? This word is very important.
Minus M.
Inertia.
Exactly. Times would be the distance from the neutral axis until the deck and divided by the inertia. How do you think it's going to take you to calculate the inertia in this case? It's going to be short, quick, or very long for this case? Do you think it's a good idea for me to give you a calculation of the inertia for this case? Ms. Santos, what do you say?
It's very long.
Very long, because you have many elements, right? So you have depth, side, bottom. It's possible, for example, for efficient vessels that the bottom is not flat, some inclination. And then you have longitudinal bulkheads, you have probably double bottom, then you have stiffeners, longitudinal stiffeners, so that's a lot of information. The secondary, how do you calculate the sigma x2? Mr. Hidro? How do you calculate it? In a very quick way, how do you calculate this?
The normal stress divided by the area.
No. Remember, this is bending. This is bending. In an extremely simple way, you could assume that this is a stiffener, is clamped here and here. If I give you force per unit length, what would be the maximum bending moment in this beam? On both ends, Mr. Ortega, Andres Ortega, what would be the maximum bending moment? This value here. What would be this guy?
Good morning, doctor. Is the 4 by the length of the multiply the length square
Of the span
divided by
square
12.
divided by
12.
by 12, yes. How about in the center?
This is the same divided by 24.
Thank you. So it's going to be that value of the moment times the distance from the neutral axis to the plate and divided by inertia. Calculate inertia, in this case, remember, you have to include what? To calculate inertia. What do you have to include here? Ms. Arechua. What do you have to include here to calculate the inertia of the stiffener? Ms. Arechua?
Yes, doctor. In the inertia,
To calculate inertia, yeah. It's typical of this secondary behavior. What do we have to include here? Now, Miss Leon, Caroline Leon, do you remember what do we have to include?
The effective span.
Yes, the effective breadth. Yes.
There.
So you take the effective breadth, consider the web, the flange of the reinforcement, evaluate the inertia of that, and proceed to calculate the stress. Okay, and finally, how about in the tertiary stress? Mr. Benavides, what do you need in order to calculate the stress for the plate, the tertiary stress, Mr. Benavides? What information do you need?
Good morning, doctor. We want to determine the maximum bending moment in this case, in the shortest direction of the plate.
Exactly, the shortest direction. And what information do you need to calculate that? What parameters influence the result, which is the bending moment? What parameters do you think do you need? No?
No.
Now, Mr. Romero, Jandri Romero, what information do you need to calculate this guy here?
Good morning, doctor. And thickness and the moment.
Yeah, but I'm interested in the moment. What information do you need to calculate the moment?
Moment Y.
That's
That's
not
right.
my question. My question is, what information do you need to calculate the moment?
Maybe can be if we use the Timoshenko's
Yeah,
table,
but what information do you need?
the pressure and the dimensions of the plate.
Exactly. So it's the pressure, the plate aspect ratio, the minimum dimension, B or S, whatever, according to the classification society. Yeah. And then you get the maximum bending moment. Then you have the thickness, and the result is going to be the stress. The top or on the bottom. Remember, we have to be careful because in this case, when we combine, we'll see that in a minute, the signs are very important, okay?
Excuse me, doctor, I have a question.
Yeah.
What thickness we have to consider in the tertiary behavior at the center or at the side?
I don't think you're gonna have much of a difference. The plate, the thickness is gonna be uniform. Definitely.
Can you repeat again? I couldn't listen.
If you analyze this plating, probably the plate, the thickness of the plate is going to be uniform.
But in the last example, the thickness of the side was very higher than the thickness of the middle, of the center.
Yeah, but what you can do is you can, for example, you want to analyze this plate here, the thickness of that plate is going to be uniform. And then if you analyze it in here, in the center line, the thickness will be smaller, but for this plate, the thickness will be uniform. So you want to analyze, this is the section. You want to analyze this plate, then the thickness of that plate, yeah, will be a little bit higher than the plate here. But for this plate, the thickness will be uniform. Then you want to analyze here, yeah. The thickness will be another value, but on each panel, the thickness can be considered as uniform.
So we could use the thickness of the center.
Of the what?
The thickness of the center on Timoshenko, when we do that?
No. If you have one thickness here, use that one for the side. If you have another thickness here, use that value for the plate at the center. So what I'm saying is that on the deck, this question here. You want to analyze the plate at the center. Probably here, shear stress will be null. If you analyze the thickness here, okay, on the side, the shear stress will be interesting. And the normal stress will also be interesting. So the thickness here will be higher than that one. But if you analyze the plate in the center, you take its thickness and consider it as uniform. If you want to analyze the plate on the side of the deck, okay, yeah, you have to look it up in the plan, I'm sorry, and see what the value for that thickness is, and consider it as uniform.
Okay, doctor, thank you.
You're welcome. Okay, now this is very general, just one slide about this. This is what we call limit states. Okay, a limit state is related to the conditions for potential failure. And this potential failure means that something that prevents the ship from completing its duty. Okay, for example, okay, what's the limit state considered in service? Okay, that means that during the service, okay, you have pressure, you have the weight, the ship moves because of the dynamic pressure. And all of that is what we call the limit state in service, right? Another case is the ultimate limit stress. That's what Engineer Isaac is analyzing, okay? So let's pretend that there is an extreme situation and that takes you to the collapse of the structure, okay? But that's an extreme. For example, what happens in the case of the ship when it sails in very large waves, right? In this situation, right, the deck plate is in compression. And you remember probably that Professor Troches last week, he was talking about the possibility of buckling of the lower structure, right? That's the limit because once it buckles, basically it just leads to collapse of the structure. Okay. Fatigue. Okay. There are many pieces of the structure which the loading is very low, but this load is applied with a changing sign like this. Trick, track, trick, track, trick, track. So this allows the fatigue to develop. That reduces the strength, generates a little crack. This little crack grows, and eventually this crack is so large that the structure doesn't have enough strength and fails. And finally, the accidental limit state. Okay, for example, the ship comes to a pier, right? And it just slowly touches the pier. Is this the way it happens? No. Usually the tug pushes the side of the ship and it's just get closer and bangs the pier. But that generates an axial or a transverse load, concentrated very high load. That's not a service. That's an accidental limit. And you have to think in each one of these if you want to design a safe structure. Okay? That's why for the plate thickness in the classification society, we have two formulations. One is for considering the pressure. And what I interpret is that that's the service limit state. So the ship works, travels from one port to another, and it oscillates. So you have a lot of pressure, dynamic pressure acting on the plating. Okay, that's a common situation. But also you have to consider for the same plating, you have considered a possible accident. That means that you have to consider that this plate could be in this limit state. So you have to have two formulations and you have to select the thickness. So you are covered in both cases. Okay, that's something which is very interesting. Okay, of course, if you go to the engine room, right, probably you will be much worried about fatigue. Okay, if you go to a deck plate, for example, okay, because of this primary hull bending, okay, yeah, you apply a load on the deck, but you also have to be worried about the possibility that this compression generates buckling, and that takes the ship to the collapse. So these are extreme cases that you have to be worried about. Okay, now, how can failure occur? Okay, there are many authors and there are many opinions. This is just, I just took it from ship design and construction, right? They consider that there are three ways that the structure can fail. One is because of yielding, right? It's the simplest. 235, that's it. You reach 235 and consider that the structure has failed. Why? Because when you take the load out of on the structure, there's going to be a permanent deformation. Okay, so that's just coming into plasticity region, either in tension or compression. The other possibility is the possibility of buckling. Okay, every time you have something like this in compression, right, the no deformation is unstable. That means that the structure will try to get away from that situation because that situation is unstable. Right? It's like having a little hill and you put the ball on the top, on the crest of this hill. You just blow a little bit and the ball will roll away from that situation because this situation is an static equilibrium, but it is unstable. Okay, so that's why every time you have a member in compression, okay, every time you have a member in compression, you have to check if the stress that you're applying is below the critical stress. Because if you reach the critical stress, that means that the element is not going to be held in the horizontal position. He will try to get away from that situation. And the problem with that is that the strength of this element is going to be reduced. So since that's reduced, somebody else will have to take its task. And that problem, this other element will also probably will fail too. So it is like a cascade, and eventually the structural collapse. Okay. And finally, fracture. Fracture means that you have two elements which are separated. And that's several cases, including, for example, low cycle fatigue. That's very interesting, right? Because that means that you have a low limit, a low stress value, but this stress is changing in sign, positive, negative, positive, negative. Okay, that leads to the generation of cracks, and that crack grow, and eventually there's some fracture. So basically, those are the three modes of failure. Some researchers, some engineers like to consider also as a mode of failure the low stiffness. Okay, for example, you have a tower, and here you have an antenna, right? The wind blows, so the tower deforms. If it deforms, the antenna moves, and if the antenna moves, the connection, because you're receiving a signal, the connection is not here anymore. So you lose connection. The stresses are below the yield point. There is no buckling. There is no fracture. The problem is that there is a lot of deflection. Okay, so some authors include in the modes of failure the lack of stiffness, but in this case, I just looked it up in the ship design construction book. They didn't consider that. Okay, but there's some disparity between knowledge. Okay, so in our case, usually we consider the first two, usually, right? Yielding, and so we have to do a check. If you have repetitive loading, you have to do a check of fatigue also. Okay, that's a general comment. Now, in the previous slide, we showed that there are possibility of combining. Okay, for example, in the X direction, we could have primary, secondary, and even tertiary stresses in some cases. Okay, but if we have X and Y stresses, how do we combine them? That's what we are trying to answer with one slide. Okay, this maybe you recognize, no, you should recognize that this is the result of a simple tension test. Okay, let me write it here. This is a simple tension test. So you have something like this, okay, and you pull it in this direction, and you pull it in the other. So basically here, you have only one stress, which is sigma x. So that's the only of the stress that you have. There is no sigma y, no sigma z, etc. Okay, so here you have sigma x, this is sigma x, and this is epsilon x. And you see that if you are here, that's 0.2, that's the yield stress. If you are below that, that means that after you take the load out, you come back to the original state. You come back here. If you go apply a force which takes you above the yield point or the elastic limit, there's going to be, after you unload the structure, you have a permanent deformation. Okay. In this case, you have two curves, red and blue. In the red one, it's a classical one. We call it engineering stress. And we use the original, this is original area, A sub 0 is the original section to calculate the stress. So you divide P by A sub 0 and you obtain the red curve, right? Because when you pull, there's going to be a reduction in the normal direction because of the Poisson effect. The area will be reduced. So if you use this area, you obtain the blue curve. And you see that since the area reduces, the stress it's higher than the red one. So this is the result using the actual, the real area. Okay, that's why we call it A. So that's the difference between these two. In the case of the red curve, we recognize the maximum stress one is that what we call the ultimate strength, right? State, the ultimate limit state. If you apply in this situation a value of stress higher than sigma 1, that means that the structure cannot sustain that. Basically, we can expect a collapse of this specimen. Now, in this case, if we are below sigma yielding, okay, so if we are from here and below, we are safe. So there is no failure. So in this case, simply, if sigma x is below sigma yielding, we are safe. That's it. Now, the problem is that what happens if we have more than one value of sigma or more than one direction? For example, sigma x and sigma y. Okay, we're going to answer that when we return. Isaac, would you please stop the recording so we could have a